I'm trained as an architect. I did my master's in both architecture and computer science, and now I'm back in the Department of Architecture, but at the Institute for Computational Design at the University of Stuttgart. So at our institute, we basically do research at the intersection of computational design, digital fabrication, and biomimetics. So we use computational tools to algorithmically generate our designs, which are then, we manufacture them using large techniques to make these designs physical. In larger scale, it includes CNC machines and robotic arms, and in a smaller scale, usually 3D printers. And and a common thread between all the research at our institute is bioinspiration. So we take inspiration from nature and implement it with our design and fabrication processes. At ICD, I work at the Material Programming Research Group, where me and my colleagues, Tiffany, Laura, and Dylan, we work on shape-changing structures. So our work is mainly designing and fabricating hygromorphic structures, which are structures that respond to the moisture or the relative humidity. Now, of course, these structures, their shape change does not rely on electromechanical sensors or actuators. Instead, it relies on the material properties and structuring itself. So our research is highly inspired by nature, and I'm pretty sure that you guys have already seen this example, the famous pine cone, which is still a perfect example of hygromorphic structures. So when these cones are attached to a tree, the scales are closed to protect the seeds. And when the right time comes, they fall off from the tree, and as they dry, these flaps open to release the seeds. And the cool thing is that this process is fully reversible. So if you put the cone back in the water, it closes again, and as it dries, it opens again. And this cycle can happen many, many times without requiring any metabolic energy. So this research on hygromorphic structures started at our institute almost 10 years ago. And they began with using natural wood as the hygroscopic material to create hygromorphic structures. So what we're looking at here is a bilayer structure, which is composed of wood on one side and glass fiber on the other side. And together, they create a bilayer structure that translates volumetric expansion of wood and its cellulosic material into bending. And this wood composite or veneer composites can be actually programmed to respond in different ranges of humidity. For example, here you're looking at two structures that are programmed differently, one to be flat when it's dry and one to be bent when it's dry. And basically with wood, this type of programming is very easy. It all depends on which state the wood is at and what moisture content it has when you laminate it to the restrictive layer here, the glass fiber. So this system has been applied in a controlled environment. Here is the hygroscope exhibition piece that was exhibited in the Pompidou Center in France, where there's basically a chamber where the humidity can be controlled, and these elements open and close in response to it. And the same system has also been applied in an open environment in this architectural scale pavilion, where these aperture-like elements respond to the weather conditions to allow adaptive ventilation. So wood material can also be used in much larger scale to create self-shaping structures. For example, what we're looking at here is a piece of wood, 1.5 meters, almost 4 centimeters of thickness, and it takes around 3 weeks for it to go from flat to bent. So this is conceptually different than the thin elements that we saw previously. Here, the self-shaping is basically used as a manufacturing technique to create one-time self-shaping large-scale structures. For example, it was used here in building this Orbach Tower, which is a permanent building somewhere in the south of Germany. if you're here, you can go and visit it. And all the panels in these buildings are self-shaped wood that had been also mechanically locked so that the building doesn't change its shape when it rains. But then using natural material like wood also comes with some limitations, some restrictions. Because it's a material that is found in nature, it's like anisotropic material structuring, basically the arrangement of the cellulose microfibrils inside the wood is already predetermined. And as we know, this type of structuring is what determines the shape change. So for example, if we want our piece, our bilayer, to bend in a specific way, like a specific bending orientation or direction, what we need to do is to look for a piece of wood that has that specific material arrangement. And here you look, for example, an example of one of the master's students who was trying to create a more complex curvature in this curve folded modules. And in order to reach this curvature, he needed to pick different pieces of wood from the timber and then arrange them together in a puzzle. And of course, this process requires a lot of manual work. And this then brings us to 3D printing. With 3D printing, we are basically able to create the structure of the wood layer by layer, line by line, and reconstruct the material structuring ourselves. So specifically when I'm talking about 3D printing, our work is based on using FDM 3D printers, normal desktop FDM, and then as a material, we use filaments that are either commercial wood-filled filaments or customized cellulose-filled filaments. So in these filaments, basically the wood or the cellulose content, which should be around or higher than 30%, would then bring this hygroscopic property and allow us to create responsive and shape-changing elements. And then with 3D printing, then we are not constrained just reconstruct the natural material composition of wood, but we can now then combine different materials with different properties, flexibility, and pattern them the way we want to achieve different functionalities. So then basically 3D printing or 4D printing in this case lets us really design and engineer our shape-changing structures in different length scales, from micro scale, which is material, to meso scale, to macro scale. So with materials, filament materials can be engineered based on different polymers or different fillers to have a similarly responsive property. And then the mesostructure can be arranged to have controlled anisotropy and porosity, which then physically programs the shape change. And then lastly, various kinds of mechanisms can be designed for specific functions. And the last two are highly utilized by computational design for digital fabrication processes. So now for the remaining of my talk, I'm going to be focused on 3 studies in which I will be focused on each of these aspects of material, mesostructures, and mechanisms. So the first study on materials was a research project that we conducted in collaboration with the Institute for Plastic Technology at Uni Stuttgart. And here we were able to create our own custom filaments. So in order to create the hygromorphic filaments, we picked cellulose as the filler to bring the hygroscopic property, so cellulose powder. And then we tested different matrix polymers, such as bio-based TPU, bio-based PK. We were specifically using bio-based polymers for sustainability and using bio-based basis for the materials. And now, what this this process brought to us is that we were suddenly able to create a range of different filament materials. For example, flexible active materials, which were produced by mixing bio-based TPU with the cellulose content within the TPU, or PA, which is basically nylon. And then within this process, we were then able to produce a palette of filament materials, active and restrictive, stiff and flexible materials, which we then used to 3D print our hygromorphic structures. So unfortunately, at this point, I cannot share too much because this is now a paper that I need to submit this week. But what I can say is that the 3D printing material, the 3D printed structures, which are produced by the cellulose film filaments, are super responsive to humidity, not only to water immersion. They are relatively fast, so they change shape something between like 20 minutes to 40 minutes in the absorption and desorption cycles, and their motion is also cyclic. And then, of course, because we're doing 3D printing, we can simply program different geometries, different bending curvatures, bending orientations, and etc. And I'm sure that you guys already know these topics well. So in the next study, we were more focused on the aspect of mesostructure. So this was a project that we did in collaboration with biologists and also engineers from Uni Freiburg and Uni Stuttgart. And our aim was to program the time scale of motion and the sequential motion steps in hygromorphic structures. So at the early stages of the project, the biologists showed us this plant, which when it rains, these silver thistles close to protect the seeds. But what is super interesting is that the movement of the thistles, they don't all move at the same time, but they move sequentially. So some of them first, and then the next layer, and then the next layer. And then through this sequential motion, they avoid colliding with each other and getting clogged. So then we set it as our aim to be able to create the same sequential motion in our 4D printed structures. And the way to do that was to arrange the mesostructure and play with the 3D printing parameters. So the idea here was that hygromorphic shape change depends on the rate of moisture absorption and desorption. And we can delay or fasten this rate by changing the thickness and the porosity of the active layer, which is controlled by the number of active layers and by the spacing parameter. So this spacing parameter is basically the distance between two printed paths. And the third strategy that we devised was to add a blocking layer, basically to print a layer with a flexible TPU material on top of the structure to completely block the water absorption and desorption from one side. And then in the next step, we tested different parameters. So basically tested changing the number of layers, the spacing, and adding the blocking layer with different modulated porosity. And we took time-lapse images to record both the time of shape change and also the curvature. And here is a recap of the results or of the effect of each of these parameters on the time scale. So as you can see, with the changing the thickness, there is a huge change in the time scale. Similarly, with changing the porosity, we have a variation in the time scale, and also with adding the blocking layer, we again have a huge delay. So we then use these techniques, these parameter adjustments to create first basic structure, here an aperture that we are just showing how different flap elements can bend in different times. And then later on, we use this technique to create this long bending cantilever. So this structure is so long that if everywhere bends at the same time, it just collides with itself. But with programming 3 different areas that each bend at different time steps, we can create this nice like spiral motion and spiral shape at the end. And then in the last step, we thought we can add a lock into our cantilever. So basically, after the cantilever goes and rolls around itself, it inserts that lock element at the end and stabilizes its ship fully and self-locks. So here it got really tricky because both the timing needs to be programmed and the geometry, the kinematics also needs to be very precisely programmed so that the lock element and the open slot meet at the exact right time and in the right point in space. And here you can, oh, sorry, I think the video got weird. Yeah, here you can see the locking element self-shape. I don't know why the video got jumpy, so let me play it again. Yeah. So yeah, at the very last time step, the lock elements bend outwards to finish the mechanism. And then the last study that I want to share with you is a study on mechanisms. So here we were thinking of now how can we go beyond simple bending and create more exciting and intricate type of structures with enhanced functionalities. And we came across a specific type of structures, geometries, which are curved crease folding. So curved folding inherently combines bending and folding at the same time. It's not like the straight crease origami where the whole shape change happens on the hinges, but in curved crease, as the hinges fold, the faces also bend. So our idea was to let's initiate folding through bending of the faces. So our fold lines are completely passive, are basically just flexible hinges. And by bending the faces, basically the whole structure buckles and folds in itself. Here you can take a look at the structuring of different materials in different layers. You see the two bilayers with the opposite arrangement of active and passive layer to create convex and concave bending on the two sides. And you see those white strands, which are the flexible strand that creates the hinges. And here we take a look at how the fold angle can be programmed. So we found two methods. One is purely through geometry by changing the curvature of the crease lines, as you see in the right-hand side and top. And second is by changing the printing parameters, which affects the curvature. So then by inducing less curvature on the faces, we can get less folding angle on the hinges. And one cool thing about this type of self-shaping curve folding structures that we were really interested about was the motion, what we called motion amplification effect. For example, here you look at two exactly same materials and mesostructures. The only difference is in the geometry, in the mechanism, and you see the curve folded one shrinks much more after the folding, which is very useful, for example, in the use case of putting these structures on the building skins in architecture, as we saw in the early examples, like in the Hygroskin pavilion. To take a look at our workflow, so we usually work in Rhino and Grasshopper. We are architects, and this is kind of our favorite tool. So our typical workflow starts with arranging the mesostructures. So here you can see the red and the blue surfaces, which are identifying the convex and concave bending curvatures. And you see the lines which indicate the anisotropy and basically the bending orientation. And after the mesostructure setup, we usually have a step of simulation to see how the shape change will happen and how it affects the overall structure. And then if we are happy with the way that everything looks, we go and automatically generate the toolpaths. So these toolpaths are directly correlated, directly connected to the mesostructure setup that I showed in the first step. And then at the end, we get the G code and we give it to our 3D printer. And then we print these structures using our wood field filaments. Here is our is the bird, this folded bird structure that you just saw on the 3D printer. Oh, I'm sorry, the video got glitchy again. I am not sure why this is happening. I'm sorry about that. But what we just looked at is the basically self-shaping process of this structure. This is printed with the commercial filament, the commercial labeled metal 5 filament. I think you can buy it online. It's produced in Germany, but you can also buy it. And with this specific material, it's slightly strange. It kind of requires a priming stage, which includes putting it in the water for around half an hour. And then after you take it out from the water, as it dries out, it folds itself. So what you saw is that with the bread structure is basically folding and self-shaping upon drying. And with this type of material, if we then put it back into the water, it goes back into flat. And then if we let it dry again, it gets folded. And then now that we have the setup of this workflow, we can also go towards more complex crease pattern, such as the tessellations, as you see here, and here a video of this tessellated structure upon folding. Here, I think is a time lapse that took around 12 hours with this material. And then this is just to for one moment to think that actually folding curve folded structures are really, really difficult. Either if they're by hand, they need really an artisanship, or if you want to fold them with the robots or machines, even more complex. But then using this method of self-shaping in 4D printing, this whole folding process is basically embedded within the material itself. And these structures are also surprisingly strong, very strong. So for example, on the left-hand side, a structure that is 1 millimeter thick and 8 grams of weight, it can take 620 grams of load on top of it. So to recap, through 3 studies, I tried to show how hygromorphic 4D printing can consist of optimizing or customizing and designing materials, mesostructures, and mechanisms. With materials, I showed how bio-based polymers and biofillers, such as cellulose, can be used to create active filaments. With the mesostructures, I showed how FDM toolpath parameters can be adjusted to program the shapes, not only in terms of their geometry and kinematics, but also the timing and the sequences of motion. And lastly, I showed a new type of mechanisms that brings interesting and exciting opportunities with itself. And just to give a hint of what we are doing right now at the moment, actually, in the past 9 months, I and our team of material programming has been extremely busy with trying to bring this research into real-life application. There is a building that's going to be constructed at the University of Freiburg in Germany, and there will be a window, a 12 square meter window, or like a facade part on this shell, which will be hopefully filled by the 4D printed hygromorphic structures, which act as adaptive shading elements. They respond to the weather conditions and they open and close to provide shading and regulate the heat gain of the building. So this is really exciting, really intense, because suddenly when we are now want to actually put it out in the real life, we need to consider many different things, such as the effective UV, weathering conditions, lifetime, duration, durability, and etc., which is very exciting. So I think I took 25 minutes. So I hope it was okay.
Yeah.
And I'm now open to questions.
Thank you so much. Yeah, Yasmin, really impressive work. And folks are already saying amazing and fascinating.